Tonight, while you lie back and close your eyes, let the universe do the heavy lifting for your brain. We're going to drift through calm, simple, mind-bending facts about space, from the size of the cosmos to the tiniest traces of its beginning, explained in normal language you don't have to work to follow. Your job is just to listen, let your thoughts stretch a little farther than Earth, and if sleep starts to pull you away mid-sentence, that's exactly what this video is here for. But before we continue, please subscribe to the channel to give your support. Let's continue. Here's a question that pushes your brain. How big is the universe you live in right now? You hear that the universe is about 13.8 billion years old, so the simple guess is maybe it is about 13.8 billion light years across. That sounds neat, it feels logical, and it is very wrong. The part of the universe you can see, the observable universe, is not 13.8 billion light years wide. It is roughly 93 billion light years across. The most distant galaxies whose light reaches you today sit around 46 to 47 billion light years away in every direction, even though their light has only been traveling for 13.8 billion years. That does not break the speed of light, it tells you something else. The arena itself, space, has been stretching while the light is on the way. Light in a vacuum moves at about 300,000 kilometers per second, around 186,000 miles per second. If space were fixed, you could multiply that speed by 13.8 billion years and get a simple distance. But space is not fixed, it expands, and it has been expanding for the entire history of the universe. While a photon travels toward you, the distance between you and the galaxy that emitted it increases because the fabric of space in between is stretching. You see that galaxy as it was billions of years ago, when it was much closer, but by the time the light arrives, the galaxy has ridden the expansion of space to a much larger distance. When you talk about the size of the observable universe, you are really talking about how far those galaxies are now, not where they were when the light started. Now ask the next question. Inside that 93 billion light-year wide bubble, how much is actually in there? For a long time, astronomers thought the number of galaxies was huge, but still kind of manageable, around 100 to 200 billion. Then, deep sky surveys changed the picture. Telescopes stared at tiny, dark pieces of sky that looked empty and found thousands of faint galaxies in those small regions. Adding all that up, the estimate jumped to around 2 trillion galaxies in the observable universe. Each of those galaxies holds a massive population of stars. Big galaxies contain tens of billions, often hundreds of billions, and in some cases, more than 1 trillion stars. Multiply that across all galaxies, and you get a total star count around 10 to the power of 22 to 10 to the power of 24. You do not need the exact number, just know that if you tried to count those stars, one per second, without stopping, you would need far longer than the age of the universe, and you still wouldn't finish. So in a universe with that many galaxies and stars, what does your local patch look like? Where exactly are you in this structure? Your real address is much smaller than your brain expects. You live in the Milky Way galaxy, a barred spiral roughly 100,000 light years across. In kilometers, that's about 1 billion kilometers. If you tried to cross that distance in a fast spacecraft, moving at tens of thousands of kilometers per hour, you would need much longer than the entire age of the universe. On human timescales, your own galaxy might as well be infinite. To make that more concrete, think in simple size steps. Take the Milky Way as a disk 100,000 light years wide. The solar system, the region where the sun dominates, out past Neptune, is a tiny patch inside that disk. If you tried to mark it on a drawing of the galaxy, it would be too small to see. Every planet you know, every probe we have launched, every radio signal we have sent sits inside that tiny region, in one spiral arm of one galaxy among trillions. And even that patch is not sitting still, it's moving inside something bigger. The Milky Way is part of a small collection called the Local Group. This group includes our galaxy, the Andromeda Galaxy, and a few dozen smaller dwarf galaxies spread across a region about 10 million light years wide. On that scale, gravity between the galaxies is strong enough to beat the overall expansion of the universe. Instead of sliding apart with the rest of space, the big galaxies in the local group are moving toward each other. Andromeda makes this very clear. It's on a collision course with the Milky Way. Right now, it's about 2.5 million light years away and closing the gap at around 110 kilometers per second, roughly 250,000 miles per hour. Take a highway speed of 110 kilometers per hour, about 68 miles per hour, and multiply it by more than 2,000. That gives you the speed of an entire galaxy of hundreds of billions of stars, gas, dust, and dark matter moving straight toward you. The first close pass and major merger are expected in about 4 to 5 billion years. When that happens, the two spirals will pass through and around each other several times. Their disks will distort, long streams of stars will be pulled out, and over billions of years, they'll settle into a new, larger galaxy. Direct star-star hits will still be rare because stars are separated by huge distances, but their orbits will be reshuffled, gas clouds will crash, and bursts of new star formation will switch on. Your local group is not a static island, it's already falling together under its own gravity. If this much drama is guaranteed inside just 10 million light years, what does that tell you about the universe beyond it? Here's the next step. Everything you've heard so far, the Milky Way, the coming Andromeda collision, the entire local group, all of that sits inside only the part of the universe you can see. When cosmologists say observable universe, they mean the region around you from which light has had time to reach you since the Big Bang. Today, that radius is about 46 to 47 billion light years. That distance is a horizon. Beyond it, light and any signal simply haven't had enough time to get here. The universe almost certainly doesn't stop at that horizon. As far as current measurements show, space keeps going in all directions, beyond the observable edge. It may extend for many times the radius of the observable universe, or it may be effectively infinite. Regions beyond your horizon can have their own galaxies, stars, planets, maybe even life, but you'll never know about them because the expansion of space is carrying them away faster than any light beam or spacecraft can ever close the gap. Even a ship cruising just under the speed of light can't outrun the expansion of the universe itself. So when you say the universe in normal conversation, you're usually talking about something smaller, the observable bubble around you. That bubble is already extreme for human standards, about 93 billion light years across, filled with maybe 2 trillion galaxies, each with tens of billions or more stars. And inside one of those galaxies, your entire solar system is a point too small to draw. The real universe likely stretches far beyond what you can ever observe, maybe without end, and you're locked inside one patch of it by the basic rules of space, time, and light. If just the size, the numbers, and the limits already feel like too much, the next step is even stranger, because every time you look up at the night sky, you're not seeing the universe as it is, you're always looking back in time. Here's a simple but brutal fact. Every time you look at the night sky, you're not seeing the universe as it is, you're seeing what it used to be. Light has a finite speed, about 300,000 kilometers per second, around 186,000 miles per second. That's fast, but it's not instant. And because space is huge, the delay becomes huge. Start in your own system. The sun is about 150 million kilometers away, around 93 million miles. Light from the sun takes a little over 8 minutes to reach Earth. So when you see the sun, you're seeing it as it was 8 minutes ago. If the sun vanished right now, you'd still see it shining, and Earth would still orbit normally for those extra 8 minutes. Even at this small scale, now already has a built-in lag. Go to the nearest large galaxy, Andromeda, about 2.5 million light years away. 1 light year is the distance light travels in 1 year, roughly 10 trillion kilometers. When you look at Andromeda in a telescope, you're seeing it as it was 2.5 million years in the past. At that time, early humans on Earth were using stone tools. The image in your eyepiece and the real state of that galaxy today are not the same thing.
Push to the edge. The most distant galaxies we see with modern instruments are more than 13 billion light years away. You are seeing them as they were when the universe was under 5% of its current age, only a few 100 million years old. These are young, rapidly forming galaxies, full of newborn stars and violent activity. On your screen, they look like tiny red smudges, but those smudges are snapshots from deep cosmic history. You never see the universe live, only delayed footage, and the delay can be more than 13 billion years. So if every direction you look is old news, what does right now even mean for the universe? Here is the disturbing answer. Right now is not a universal thing. In daily life, it feels obvious. Two events either happen at the same time or they do not. Relativity says simultaneity depends on motion and gravity. Two flashes that are at the same time for you will not be at the same time for someone moving at a different speed or sitting at a different height in a gravitational field. There is no single master clock that all of space follows. Take a galaxy 1 billion light years away. The light you see from it tonight left that galaxy 1 billion years ago. You might ask, what is that galaxy doing right now, this second? There is no unique way to link your now to its now. Different observers moving in different ways slice space-time differently and pick different sets of events as simultaneous. And even if you pick one convention, you still cannot know what is happening there now, because any signal carrying that information needs 1 billion years to reach you. You are always at least 1 billion years behind on the news from that place. Astronomers lean into this instead of fighting it. Distance becomes a timeline. A galaxy 5 billion light years away shows how galaxies looked when life on Earth was still getting complex. A galaxy 10 billion light years away shows a time when star formation across the universe was much more intense than it is today. Nearby galaxies show the recent universe. Medium distances show the Middle Ages. The most distant ones show the universe as a young, growing system. You are watching cosmic history by scanning outward. This galactic archaeology lets you track how galaxies gain mass, merge, and shut down star formation over billions of years. You can see when heavy elements build up, when central black holes were most active, when big clusters assembled. But to turn farther away looks older into precise ages, you need a way to measure how much the light was stretched on its journey. That is what redshift does. As light travels from a distant galaxy through an expanding universe, its wavelength gets stretched along with space. The light shifts toward the red end of the spectrum, which means longer wavelengths and lower energy. The more distant the galaxy, the more its light is shifted by the time it reaches you. Astronomers measure this stretching and call the result the redshift. A galaxy with a redshift of around 7 or 8 is so far away that the light you see left when the universe was less than 1 billion years old. This stretching is not just the galaxy speeding through empty space, it's space itself expanding and carrying the galaxy along. That's why the most distant galaxies can appear to recede from us faster than light without breaking relativity. They are not moving through space faster than light, the space between us and them is increasing. By combining redshift measurements with models of how the universe expands, you can turn "the spectrum is shifted by this amount" into "this light left the galaxy this many billions of years ago." Put this together and you get a clear rule. In this universe, distance and time are not separate. Looking far away always means looking far back. That sets up one more question. If motion and distance twist time for light coming to you, what happens if you start moving close to the speed of light yourself? Imagine a spacecraft that can cruise at 99.9% of light speed, about 299,700 kilometers per second. At that speed, time on the ship runs significantly slower than on Earth. This is time dilation. On board, your heartbeat, your thoughts, your clock all feel normal, but when you later compare with clocks left on Earth, they do not match. Say you fly out and back on a journey that in your ship's frame takes 10 years total. Because your time was slowed relative to Earth, people who stayed home might experience many decades during your trip. You come back 10 years older while Earth has jumped far ahead. You didn't just change your position in space, you changed your position in time relative to everyone who stayed behind. So when you stare at the sky, remember this. Every star is an old message. Every distant galaxy is a younger version of itself. And even your own clock is not absolute. In a universe where time and distance are so tightly linked, the next question is, did any signal from the very beginning survive? Any trace from when everything was hot, dense, and just starting to form? You asked if any signal from the very beginning survived. Any trace from when everything was hot, dense, and just starting to form? The answer is yes, and it's all around you right now. Every cubic meter of space around you, in your room, outside, between galaxies, is filled with ancient light called the cosmic microwave background. It's a faint glow with a temperature of about 2.7 Kelvin. That's roughly minus 270 degrees Celsius, or about minus 455 degrees Fahrenheit. Only a few degrees above absolute zero. Your eyes can't see it because it's in the microwave part of the spectrum, but sensitive antennas pick it up as a background hiss from every direction. That light comes from a time about 380,000 years after the Big Bang. Before that, the universe was so hot and dense that electrons and protons couldn't stay bound together. Atoms couldn't exist. Photons, the particles of light, constantly bounced off free electrons, like headlights in a thick fog. Space was opaque. Nothing could travel far before being scattered. As the universe expanded, it cooled. Eventually, it got cool enough for protons and electrons to combine into neutral hydrogen atoms. Once that happened, photons could move freely, the fog cleared, and light finally decoupled from matter. The glow from that moment has been traveling ever since, stretched by billions of years of expansion, cooled from a brilliant fireball to a cold microwave afterglow that still fills the universe. Here's the part that should get your attention. That microwave background is almost the same temperature in every direction. If you measure its temperature across the sky, it's uniform to about 1 part in 100,000. That means if the average is 2.725 Kelvin, the hot and cold spots differ by only a few 10,000ths of a degree. On first glance, it looks boring, just a smooth, uniform bath of radiation. But those tiny bumps, those small hot and cold regions, are the seeds of everything you see today. The slightly hotter spots mark regions that were a bit denser, with a little more matter. Gravity pulled harder there, slowly drawing in more material. Over hundreds of millions of years, those overdense spots grew into the first clumps, then into galaxies and clusters. The slightly colder spots were slightly underdense, regions that would become cosmic voids. If the initial variations had been much larger, gravity would have crushed matter quickly, forming black holes everywhere before stars and planets could form in a stable way. If the variations had been much smaller, matter wouldn't clump efficiently, and the universe would have stayed too smooth, with very few galaxies and almost no complex structure. The fact that the bumps are at this specific tiny level is what allows stars, planets, and you to exist at all. Now ask this. How can a faint, almost uniform glow with tiny temperature differences tell you detailed facts like the age of the universe, its composition, and even the overall shape of space? That's exactly what satellites like COBE, WMAP, and Planck were built for. COBE, launched in 1989, first confirmed that the microwave background had the almost perfect spectrum expected from a hot Big Bang, and it detected the first rough map of those tiny fluctuations. WMAP, launched in 2001, sharpened that map, showing much finer detail. Planck, launched in 2009, pushed the resolution and sensitivity even further. By analyzing the size, distribution, and strength of the hot and cold spots across the sky, scientists can fit cosmological models and extract key numbers. That's how you get the best estimate that the universe is about 13.8 billion years old. The same data tell you how much of the universe is normal matter, how much is dark matter, and how much is dark energy. And they also show that on very large scales, the geometry of space is extremely close to flat, not curved like a sphere or like a saddle. In simple terms, if you draw an enormous triangle across billions of light years, the angles add up to almost exactly 180 degrees. A random glow pattern would not do that, but the pattern we see matches a specific, precise model of an expanding universe with dark matter and dark energy built in. Here is another twist. That pattern in the microwave sky is not random static,
It is frozen sound. Before 380,000 years after the Big Bang, the universe was a hot plasma of protons, electrons, and photons all mixed together. Photons pushed out, gravity pulled in, and this tug of war set up pressure waves, real sound waves, in that early plasma. These waves moved at about half the speed of light, compressing and rarefying regions of matter and radiation. When the universe cooled enough for atoms to form and photons to decouple, those waves effectively stopped, and their pattern was imprinted in the microwave background. The size of the typical hot and cold patches and the way their sizes repeat in the data encode the frequencies of those ancient waves. When scientists plot how strong different patch sizes are, they see a series of peaks, like the resonant tones of a drum. That is the acoustic signature of the early universe. In other words, when you listen to the CMB data with the right analysis, you are picking up the first pressure ripples that ever moved through the cosmos. All of this ties into one more key question. What elements did the early universe actually make, and what had to wait for stars? In the first few minutes after the Big Bang, the universe was hot and dense enough for nuclear reactions to run. Protons and neutrons collided and fused into light nuclei. This process, called Big Bang nucleosynthesis, produced mostly hydrogen and helium, plus trace amounts of deuterium, helium-3, and a bit of lithium. When you combine what the CMB tells you about the density of normal matter with measurements of these light elements in old gas clouds and ancient stars, you get a consistent picture. The early universe ended up with about 75% hydrogen and 25% helium by mass, plus tiny fractions of those other light nuclei. Heavier elements like carbon, oxygen, silicon, and iron did not come from the Big Bang. They had to be built later, inside stars over billions of years, through fusion in stellar cores and in explosive events like supernovae and neutron star mergers. That means the hydrogen in your body is Big Bang material, but the carbon in your cells, the oxygen you breathe, the calcium in your bones, and the iron in your blood were all made later in stars that lived and died long before the sun formed. The microwave background is the record of the universe right after it became transparent. The distribution of light elements is the record of the first few minutes. Together, they show you that the universe remembers its own birth cry in precise detail, and it used those tiny imprints to grow every galaxy and star you see today. So now you know this. The universe is not just big and old, it is also carrying a detailed memory of its first moments, written into the radiation around you and the matter inside you. But the places where that matter collected, the galaxies that formed out of those tiny fluctuations, are not calm, gentle systems. On the scale of galaxies, gravity, gas, and dark matter turn that smooth early universe into something violent and chaotic. And the next step is to see how those star cities really behave when you look closely. When you picture a galaxy, you probably imagine a calm, elegant spiral just hanging in space. But that picture is wrong. On the scale of a galaxy, everything is moving too fast, smashing together too often, and powered by things you cannot see. A galaxy like the Milky Way looks stable, but if you only count the visible matter, gas, and dust, it should have torn itself apart a long time ago. Take the rotation first. In a simple system, the farther you go from the center, the slower objects should orbit. Planets around the sun do this. Mercury is fast, Neptune is slow. But in a spiral galaxy, the stars in the outer regions move at almost the same speed as the ones much closer in, around 200 to 250 kilometers per second, roughly 450,000 to 560,000 miles per hour. If only the visible stars, gas, and dust were there, that outer material should not be able to hold on. The galaxy's gravity would be too weak. The edges should be flying off into intergalactic space. When astronomers measure these rotation curves, plotting orbital speed versus distance from the center, they see them flatten out, not drop. That is a direct signal that most of the mass is not in the bright disk at all. There has to be a huge halo of invisible matter surrounding the galaxy, adding extra gravity. That unseen component is what we call dark matter. You don't detect it by light, you detect it because without it, galaxies simply don't stay bound at the speeds we measure. The shape of those rotation curves is one of the strongest, cleanest clues that most of a galaxy's mass is invisible to your eyes and to normal telescopes. Now, if each galaxy is a spinning disk embedded in a massive dark matter halo, you might hope they at least stay in their lanes and keep away from each other. They don't. On cosmic timescales, galaxies constantly collide and merge. Right now, the Milky Way is actively stripping and absorbing small satellite galaxies, like the Sagittarius dwarf. With large telescopes and precise star surveys, you can see long, thin streams of stars wrapping around the Milky Way, stretching hundreds of thousands of light years. Those streams are tidal debris, the shredded remains of smaller galaxies pulled apart by gravity. You see the same thing across the universe. Some systems show obvious double or triple cores, distorted spiral arms, long arcs of stars flung far from the main disks. Those aren't rare exceptions, they're normal stages in galaxy growth. Big galaxies become big by eating small ones, again and again. Your own galaxy has already done this many times, and it's still doing it right now. So inside those dark matter halos and those distorted star streams, what's happening to the gas that actually makes new stars? Inside galaxies, dense clouds of cold gas act as star formation nurseries. In a normal spiral galaxy like the Milky Way, gas clouds collapse and form new stars at a rate of maybe a few solar masses per year. That means the total mass of new stars per year is a few times the mass of the Sun. In more extreme systems called starburst galaxies, that rate can jump to tens or even hundreds of solar masses per year. Collisions and close passes between galaxies compress gas, trigger shockwaves, and drive furious waves of star birth. But not every galaxy is busy. Many large elliptical galaxies are red and dead. They're packed with old red stars and have very little cold gas left. Their star formation rates are close to zero. The key factor is how much cold gas is available and whether that gas can cool and stay dense. Supernova explosions, strong stellar winds, and energy from the central black hole can heat gas, stir it up, or drive it out of the galaxy entirely. That feedback can shut down star formation and keep a galaxy in a quiet, aging state for billions of years. So galaxies aren't just star cities, they're factories that can be turned up to extreme production or switched almost completely off depending on how their gas is handled. That brings you to the most controlling piece in the whole system, the center. Most big galaxies, including the Milky Way, host a supermassive black hole in their core. These black holes are not a few times the Sun's mass, they're millions or billions of times the Sun's mass. The black hole at the center of the Milky Way, called Sagittarius A, is about 4 million solar masses. In other galaxies, especially in bright quasars, central black holes can reach billions of solar masses. When gas falls toward one of these monsters, it does not just vanish. It forms a hot, rotating disk around the black hole. Friction and magnetic fields in that disk heat the gas to extreme temperatures. The system can release more energy than all the stars in the galaxy combined, in radiation and in powerful jets that shoot out along the black hole's poles at close to the speed of light. Some active galaxies shine so intensely that we see them across billions of light years, even when the rest of their galaxy is barely visible. In those systems, the central black hole is effectively controlling the galaxy's evolution, because the energy it pumps back into the gas decides whether new stars can form or not. The Milky Way's central black hole is relatively quiet right now, but that will not always be the case. Remember, the Milky Way and Andromeda are on a collision course. In about 4 to 5 billion years, they will start a long, complex interaction. Simulations show that over billions of years, the two spirals will tangle, throw out long streams of stars, and finally merge into a single, larger, more rounded galaxy, likely an elliptical often nicknamed Milkdromeda. During that process, the central black holes of both galaxies will sink toward the new common center, losing energy by interacting with surrounding stars and gas. Eventually, they will form a tight binary, then merge, releasing a burst of gravitational waves. Meanwhile, gas driven toward the core will likely ignite episodes of strong black hole feeding, turning the center into a bright, active nucleus, dumping energy into the surrounding gas. Out in the galaxy, stars will have their orbits scrambled. The sun, if it still exists then, might be thrown to a different orbit or even flung into the outer halo. From any surviving planet, the night sky could be packed with stars, the overall structure no longer a neat spiral, but a more featureless, dense swarm. So, galaxies are not calm, not balanced, and not really stable in the way your instincts expect. They are spinning too fast for their visible mass, held together by dark matter you cannot see, growing by ripping smaller systems apart, switching between bursts of star formation and long dead phases, and controlled by black holes that can outshine everything else in them. And if the engines in their centers can reshape entire galaxies, the next step is to stop thinking about galaxies at all and ask a sharper question. What actually happens right next to those black holes themselves, where space and time start to break away from the rules you're used to? What really happens if you keep going past normal gravity, past neutron stars, down to the point where even light cannot get away anymore? That is the black hole zone, where space and time stop behaving like the things you are used to and start behaving like a trap. Think about escape speed first. On Earth, you need about 11 kilometers per second, around 25,000 miles per hour, to get into space and never fall back. A black hole is what you get when you crush matter so much that the escape speed at a certain radius reaches the speed of light, about 300,000 kilometers per second, 186,000 miles per second. That radius is called the event horizon, the point of no return. For a black hole with around 10 times the mass of the Sun, the event horizon is only 30 kilometers across, roughly 19 miles. Take something with more mass than 10 suns, squeeze it into a region smaller than the size of a big city, and you have a place where not even light can get out. If you try to shine a flashlight from just inside that radius, the beam would curve back in. Space and time are bent so strongly that all possible paths inside the horizon lead inward, not outward. From the outside, you can never see past that surface. You only see the effects on nearby matter and light. An object falling toward the event horizon looks slower and slower to a distant observer. Its clock appears to tick more and more slowly, its light gets redder, and it never quite seems to cross. But from the falling object's own point of view, it crosses the horizon in a finite time and keeps going. The horizon is not a wall, it's a boundary in space-time geometry, and once you cross it, every path forward in time also moves you closer to the center. That sounds like a clean line. You are either outside and safe or inside and gone. But your body has a problem long before you hit that horizon, because gravity is not the same at your head and your feet. If you fall feet first toward a stellar mass black hole, the pull at your feet is much stronger than the pull at your head. The difference can be enormous over just 2 meters of height. Your body gets stretched along the direction of fall and squeezed from the sides. This effect is called tidal gravity, and the extreme version near compact objects has a very direct name in physics: spaghettification. For a small black hole, say a few times the mass of the Sun, the tidal forces become lethal well outside the event horizon. The acceleration difference between your feet and your head can reach thousands or millions of g, far beyond anything a human body can handle. Your bones, organs, and even individual atoms get ripped apart as you approach. You are ripped into a long, thin stream of matter before you even cross the horizon. For a supermassive black hole, with millions or billions of solar masses, the horizon is much larger, and the gravitational gradient at that radius is gentler. The pull is still huge, but it doesn't change as violently over the height of your body. In principle, you could cross the event horizon of a supermassive black hole without feeling anything special at that exact moment. Only deeper inside, closer to the center, would the tidal forces ramp up enough to tear you apart. Either way, there's no path that takes you back out. You're committed. For a long time, you could treat black holes as abstract solutions to Einstein's equations, extreme objects you couldn't really see directly.
That changed when astronomers started linking up radio telescopes across Earth to make one giant virtual instrument. In 2019, the Event Horizon Telescope released the first image of the region around the supermassive black hole, the one at the center of M87. The picture showed a bright ring of emission with a dark hole in the middle, the shadow of the black hole. The dark region is about 40 billion kilometers across, roughly 25 billion miles, bigger than our entire solar system. The bright ring is hot gas orbiting near the event horizon, heated to incredible temperatures. The size and shape of that dark shadow match the predictions from general relativity with high accuracy. The ring is not perfectly uniform. One side is brighter because gas on that side is moving toward us at high speed, boosting its light. All of this, the diameter of the shadow, the thickness of the ring, the brightness pattern, lines up with what you get when you simulate a spinning black hole with the mass measured for M87's central object, several billion times the mass of the Sun. That single image is a strong, direct test that black holes exist and that space near them is curved exactly the way Einstein's theory says. So black holes can trap light and match relativity's predictions, but there is another question. Do they live forever, or can they actually disappear? Here, quantum mechanics adds something strange. In the 1970s, Stephen Hawking showed that when you combine quantum effects with curved spacetime, black holes should slowly emit radiation. The rough idea is that the vacuum near the event horizon is not truly empty. Quantum fields are always fluctuating, and near the horizon, those fluctuations can be affected by the strong gravity. The end result, after you do the hard math, is that the black hole radiates like a very cold object, losing a tiny bit of energy over time. As a black hole emits this Hawking radiation, it loses mass, shrinks slightly, and its temperature goes up, so it radiates faster. For a stellar mass black hole, the timescale for complete evaporation is insanely long, around 10 to the power of 67 years, many trillions of times longer than the current age of the universe, which is only about 13.8 billion years. For a supermassive black hole, the evaporation time is even more extreme, with so many zeros you can barely write them out. That means there is no practical way to watch a black hole evaporate today. But in the far future, after stars burn out and galaxies fade, black holes would dominate what is left, slowly leaking energy into space. The last stages of evaporation for a small black hole would be violent, a rapid release of energy, then nothing. The universe could end up as a cold, thin bath of low-energy radiation with no black holes left at all. That is the long-term picture. Right now, black holes are not just long-lived sinks, they're active engines that shape galaxies. When gas falls toward a supermassive black hole, it usually forms an accretion disk, a flat, rotating structure. Friction in the disk and twisting magnetic fields heat the gas to hundreds of millions of degrees. At those temperatures, the gas emits huge amounts of X-rays and other high-energy radiation. Some of the inflowing matter does not fall straight in. Instead, magnetic fields can channel it into narrow jets that shoot out along the rotation axis of the black hole at speeds close to light. These jets can extend for hundreds of thousands of light years, punching far out of the host galaxy into intergalactic space. They slam into surrounding gas, heat it, and can either shut down star formation by keeping gas too hot to collapse, or, in some cases, compress gas and trigger new star formation in certain regions. The total power output during these active phases can exceed the combined light of all the stars in the galaxy. Observations show a strong link between the mass of a galaxy's central black hole and the properties of the stars in its central bulge. That correlation suggests that galaxies and their black holes grow together. When the black hole feeds, it regulates how the galaxy evolves. When it quiets down, the galaxy's growth slows. So a black hole is not just an endpoint of gravity, it's also a control knob for the life cycle of an entire galaxy.
You have now gone from stars and gas to regions where space and time themselves are bent into a trap, and where tiny quantum effects decide the ultimate fate of the most extreme objects. But black holes aren't the only places where nature pushes matter to its limit. There's another class of object, smaller than a black hole, but almost as dense, where atoms are crushed into a solid of neutrons, and the normal idea of solid material breaks down. You've seen what happens when gravity wins so hard that not even light escapes. But what if gravity stops just short of that? What if matter is crushed as far as it can go without making a black hole? That is where neutron stars live, and they push normal matter right to the edge of what is physically possible. Start with size and mass. A typical neutron star has about 1.4 to 2 times the mass of the Sun, squeezed into a sphere only around 20 kilometers across, roughly 12 miles. So you take more than a sun's worth of material and you pack it into something about the size of a city. The density is beyond what you meet anywhere else. A teaspoon of neutron star material would weigh around 10 to the 17th kilograms, more than a big mountain on Earth. This isn't rock or metal or anything you can touch. At these densities, atoms cannot survive. Electrons get forced into protons and they fuse into neutrons. You end up with a giant atomic nucleus, a star that is basically a ball of neutrons with maybe some exotic particles in the deepest layers. These objects are born in core collapse supernovae. When a massive star runs out of fuel, its core can no longer support itself against gravity. The core collapses in a fraction of a second. If the mass is in the right range, the collapse is halted by neutron pressure, and you get a neutron star instead of a black hole. The outer layers of the star are blasted into space, but the core stays behind as this ultra-dense remnant. So you're left with a city-sized object, heavier than the Sun, made of nuclear matter, spinning and magnetized. Once you have that, you need to ask, how fast can something like that actually rotate? Here's the answer: very fast. When the core of a star collapses into a neutron star, its size shrinks by a huge factor. Angular momentum is conserved, so as the radius gets smaller, the spin speeds up, the same way a figure skater spins faster when they pull their arms in. Many neutron stars end up spinning dozens, hundreds, or even over 700 times per second. These rapidly spinning neutron stars are called pulsars. At those spin rates, the surface can be moving at tens of thousands of kilometers per second. The star's strong magnetic field channels charged particles into beams that shoot out from the magnetic poles. If those beams sweep across Earth as the star spins, our radio telescopes see a series of regular pulses, like a cosmic clock. Some pulsars are so stable that their pulse timing rivals the best atomic clocks humans can make. Tiny changes in their rotation rate can be used to detect things like companions or even ripples in spacetime from very long wavelength gravitational waves. So you have a star smaller than a city, heavier than the Sun, spinning hundreds of times per second with a magnetic field that is already extreme, and the universe still has room to crank that field up even more. That brings you to magnetars. A magnetar is a neutron star with a magnetic field around 10 to the 14th to 10 to the 15th Gauss, roughly 1,000 trillion times stronger than Earth's magnetic field. At that level, the magnetic field is not just guiding charged particles, it's affecting the structure of atoms. A strong magnetar flare can release as much energy in a fraction of a second as the Sun emits in 100,000 years. We've seen sudden bursts of X-rays and gamma rays from magnetars in our galaxy that briefly outshine almost everything else in the sky at those wavelengths. So neutron stars are not just dense, they're also some of the most intense magnetic objects in the universe. And if a single neutron star can do this, what happens when two of them slam into each other? When two neutron stars orbit each other, they slowly lose energy by emitting gravitational waves, and their orbit shrinks. Eventually, they merge. That collision is called a kilonova. It produces a bright flash of light across many wavelengths, from gamma rays down to optical and infrared, and it sends out a strong burst of gravitational waves. In 2017, observatories detected a gravitational wave signal from a neutron star merger, and telescopes across the world and in space followed the light from the same event. The data showed signatures of heavy elements forming in the ejecta. Calculations and observations together say that these mergers can forge large amounts of elements heavier than iron, including gold and platinum. A single neutron star collision can produce several Earth masses of gold. The gold in your jewelry, the platinum in electronics and medical devices may well come from ancient neutron star mergers that seeded the galaxy with heavy elements, long before the Sun and Earth formed. So when two dead stars smash together, they are not just making a bright flash, they are manufacturing the rarest stuff you use. These systems are not just factories, they are also precision test benches for gravity. Binary pulsars, where two neutron stars orbit each other and at least one is a radio pulsar, give you an extremely accurate clock in a strong gravitational field. As they orbit, they emit gravitational waves and they lose orbital energy. That loss makes their orbits shrink in a predictable way. By timing the pulses, astronomers can measure changes in the orbital period very precisely. In famous systems like the Hulse-Taylor binary pulsar, the observed rate of orbital decay matches the predictions from general relativity almost perfectly. Decades before LIGO directly detected gravitational waves from black hole mergers, binary pulsars were already showing that these waves are real and that they carry away energy exactly as Einstein's equations say. Today, networks of pulsars are also used as a kind of galaxy-scale detector, looking for very low-frequency gravitational waves from supermassive black hole binaries. So, neutron stars sit at a crossroads. They are born in violent supernovae, they spin like crazy, they hold magnetic fields that push matter to the limit, they create gold and platinum when they collide, and they give you one of the best ways to test how gravity really works. But all of that is still in the category of dead or dying stars. Once you have these heavy elements and calmer environments around normal stars, the universe starts building something very different. Not just stars and remnants, but whole planetary systems. And the next question is, what kind of strange worlds fill a galaxy that has been enriched by explosions this extreme? For most of human history, you did not even know if there were planets beyond the solar system. Now, the problem is the opposite. There are too many to wrap your head around. Before the 1990s, astronomers had 0 confirmed planets around Sun-like stars. People assumed they existed, but there was no hard data. Then the first detections came in. Gas giants tugging under stars, and within a few decades, the count exploded into the thousands, with many thousands more strong candidates. These worlds range from huge, hot Jupiters that whip around their stars in just a few Earth days, to rocky worlds sitting in temperate zones where liquid water could exist. Looking at all the data, it is very likely that the Milky Way has more planets than stars, so you're talking about hundreds of billions of planets at least, maybe trillions. The default setting in this galaxy is not no planets, it is planets everywhere. And that alone should shake any idea that your own system is rare by default. One of the first big surprises was how many giant planets live absurdly close to their stars. In our solar system, Jupiter sits far out, taking about 12 years to orbit the Sun. But many exoplanet systems are nothing like that. Some gas giants orbit at distances around 0.02 to 0.05 astronomical units, just a few million kilometers from their stars, much closer than Mercury is to the Sun. They can complete one full orbit in 1 to 3 Earth days. That means a year on those planets is shorter than a long weekend. The day-side temperatures on these hot Jupiters can exceed 2,000 degrees Celsius, around 3,600 degrees Fahrenheit, hot enough to vaporize some metals. Their atmospheres can host winds blowing at several kilometers per second, faster than many bullets. These are not gentle gas balls, they are extreme weather machines that push atmospheric physics to the limit. They also tell you something important. Planetary systems can form and evolve in ways that look nothing like the neat layout you see at home. Then there are the worlds your own system doesn't have at all, but the galaxy seems to love, the super-Earths and mini-Neptunes. These are planets with masses between roughly 1.5 and 10 times Earth's mass. Some of them are probably rocky super-Earths with solid surfaces and atmospheres, but with surface gravity 2 to 3 times that of Earth. If you tried to stand on a high-gravity super-Earth and you weigh about 70 kilograms here, a scale there could read 200 or 300 kilograms. Just walking would feel like carrying another person on your back all the time, and jumping would be almost impossible. Others in that size range seem to be mini Neptunes, planets with thick gas envelopes and possibly deep layers of high-pressure ices or fluids, with no solid surface you could stand on. These classes are very common in exoplanet surveys, yet your own solar system has none. That means your local layout is not the standard template, it is one special case among many. The galaxy is happy to build planets in mass and size ranges you simply don't see here. The weirdness doesn't stop around normal stars. The first exoplanets ever confirmed in the early 1990s were found around a pulsar, a neutron star left over from a supernova. That environment has already gone through a violent explosion, but stable planets still orbit there. It's a reminder that planet formation and survival can happen in places you wouldn't expect.
Then there are red dwarf stars, far smaller and cooler than the Sun. They make up the majority of stars in the Milky Way. Their habitable zones, where a planet can have liquid water on the surface, are very close in because the star is faint. An Earth-sized planet in that zone might orbit at a distance where a year lasts only a few days or weeks. Many of the known Earth-sized planets in just right temperature zones orbit these red dwarfs, but living there would be very different. The star would loom large in the sky, flares could be frequent, and the planet could be tidally locked, with one side in permanent day and the other in permanent night. These systems are probably common, so a large fraction of any habitable real estate in the galaxy could look more like that than like your own sun, Earth setup. Finding planets is already impressive, but the next level is reading their atmospheres from light years away. One of the main tools is a transit method. When a planet passes in front of its star from your point of view, the star's brightness dips by a tiny amount. That is how many exoplanets are detected. During that transit, a small fraction of the starlight filters through the planet's atmosphere, if it has one. Different molecules in the atmosphere absorb specific colors of light. By carefully measuring how the star spectrum changes during the transit, astronomers can detect the fingerprints of gases like water vapor, methane, carbon dioxide, and others. The signals involved are tiny, changes in brightness of a fraction of a percent, sometimes less. But with precise instruments and repeated observations, they are enough to tell you what kind of air surrounds a planet dozens or hundreds of light years away. For some hot Jupiters, we already have decent measurements of atmospheric composition and temperature. For smaller, cooler planets, the data are harder to get, but telescopes are now reaching the sensitivity needed to probe them too. This matters because certain combinations of gases could act as biosignatures, tentative signs of life. For example, on Earth, the coexistence of large amounts of oxygen and methane in the atmosphere is hard to maintain without biology constantly replenishing them. In the future, if you see an Earth-sized planet in the habitable zone with an atmosphere that is out of chemical balance in a similar way, that will be a serious hint that something active is happening on the surface. Maybe geology, maybe life. So right now, you are in the middle of a shift from do exoplanets even exist to we are starting to study their weather and chemistry. The more you look, the more you see that your own world is one example in a huge catalog of possible configurations, temperatures, and chemistries. But there is a problem hiding under all of this, and it is bigger than any one planet or star. All of these worlds, all of these systems are made of normal matter, atoms and molecules. Yet when you step back to the scale of galaxies and the universe, that normal matter is only a tiny fraction of what is really out there. Most of the mass that decides how galaxies move, how structures grow, and how the universe evolves is something you cannot see at all. Here's the uncomfortable starting point. Almost everything you can see in the universe is a rounding error. If you add up all the normal matter, stars, gas, dust, planets, interstellar junk, it comes out to only about 5% of the universe's total energy budget. Around 27% is dark matter, and the remaining roughly 68% is dark energy. That means you, your planet, your star, every galaxy you've ever seen in a photo are part of a small minority component. The main ingredients of the universe are things you cannot see and do not fully understand.
That raises a sharp question. If dark matter is invisible, how do you know it is there at all? The answer is simple and brutal. Gravity does not lie. When you look at how galaxies and clusters move, the visible matter is not enough to explain what you see. Take galaxy rotation curves. In a spiral galaxy, like the Milky Way, you can measure how fast stars orbit at different distances from the center. Based on the visible mass, the stars far out in the disk should move slower, just like planets far from the sun move slower. Instead, you see something else. The rotation speed stays almost flat at around 200 to 250 kilometers per second, about 450,000 to 560,000 miles per hour, even far from the bright central region. If only the visible stars and gas were present, that outer material should not stay bound. The galaxy would fly apart. You see the same mismatch in the way galaxies move inside clusters. The galaxies are flying around inside clusters at speeds that demand much more gravity than the visible matter can supply. Put numbers on it, a typical galaxy needs about 5 to 10 times more mass than you can see in stars and gas to stay intact at its observed rotation rate. The simplest explanation is that each galaxy is embedded in a huge halo of invisible matter, extending well beyond the visible disk, and that galaxy clusters sit inside even larger envelopes of the same invisible stuff. So the dynamics say extra mass, but you still want a way to actually map where that mass is. That is where gravitational lensing comes in. General relativity says mass curves spacetime, and light follows that curvature. When light from a distant background galaxy passes near a massive object like a cluster, its path bends. Seen from Earth, the background galaxy can appear stretched, distorted, or even multiplied into arcs and rings. By measuring how strong that distortion is at different positions, astronomers can reconstruct where the mass must be regardless of whether it glows. When you do that for some systems, you get a very clear result. In the Bullet cluster, for example, you have two galaxy clusters that have collided. X-ray observations show where the hot gas is, and that gas holds most of the normal matter. Gravitational lensing, on the other hand, shows you where most of the mass is by mapping how background galaxies are distorted. The peak of the lensing signal doesn't line up with the hot gas. It lines up with clumps that are offset in positions where the galaxies have passed through each other. That tells you the main mass component barely interacted during the collision, while the gas slowed down and got stuck. The simplest reading is that there's a separate, unseen mass component, behaving like a collisionless substance, passing through almost unaffected. That is exactly how you expect dark matter to behave. At this point, you might ask, are we sure this is real matter or not just a problem with our gravity law? Maybe Newton and Einstein need to be tweaked on large scales. People have tried that. There are modified gravity theories that can reproduce some galaxy rotation curves without dark matter. But dark matter is not just plugged into one equation. Different independent observations all point to the same dark matter fraction. The cosmic microwave background, with its tiny hot and cold spots, encodes how matter and radiation interacted in the early universe. The pattern of those spots only matches the data if you include a big chunk of non-glowing matter. The large-scale clustering of galaxies across hundreds of millions of light years follows a pattern that again needs extra mass to match simulations. Gravitational lensing statistics, the way random patches of sky slightly distort background galaxies, also point to the same unseen mass fraction. Put rotation curves, cluster dynamics, lensing, and CMB together, and they converge on this story. About 27% of the universe is some form of dark matter. From all this, you can infer some basic properties. Dark matter seems to be cold, meaning its particles were moving slowly compared to light speed when structures started forming. It appears collisionless. It does not bump into itself or normal matter very often in ways that produce light. It mostly shows up through gravity. It is not made of protons, neutrons, and electrons. It is not ordinary gas hiding in the dark. Whatever it is, it behaves like a real substance with mass, spread out in halos, forming the invisible skeleton that galaxies and clusters grow on. Once you accept that, the next hard question is obvious. If it is matter, can you detect a particle of it directly? That is the goal of underground dark matter experiments. If dark matter is made of certain types of weakly interacting particles, then right now, as you sit here, huge numbers of them are passing through your body and through Earth every second, almost never interacting. To catch one, you need to shield yourself from everything else and watch for the rare, tiny recoil when a dark matter particle bumps into a normal atomic nucleus. So scientists build detectors deep underground, sometimes over a kilometer down, inside mines or mountains, to block cosmic rays and other background signals. They fill giant tanks with ultra-pure liquids like liquid xenon or liquid argon, or they use carefully grown crystals. Then they surround the detector with sensors and wait. If a dark matter particle hits a nucleus, it will give it a little kick, and that can produce a tiny flash of light, a small charge signal, or a bit of heat that the experiment can record. So far, no experiment has found a clear, confirmed dark matter signal, but each non-detection is still a result. It rules out a range of masses and interaction strengths for candidate particles. Over time, the allowed space for simple dark matter models has been squeezed smaller and smaller. New detectors are getting larger and more sensitive, pushing into regions where, if dark matter is made of the most popular weakly interacting particles, there's a serious chance of finally detecting it. Until then, you live in a universe where the main mass component is invisible, passes through you silently, and shapes the large-scale structure of everything you see. And here's the kicker. Even that invisible skeleton is not the dominant piece. There's something else, not just extra mass, but a property of space itself that is pushing galaxies apart faster and faster. Dark matter tells you your picture of matter is incomplete. Dark energy tells you your picture of empty space is broken too. What if the universe is not just expanding, but actually speeding up as it pulls away from you? By the late 1990s, cosmologists thought they had a solid expectation. The universe started hot and dense. It has been expanding ever since, and gravity from all the matter inside it should be slowing that expansion down over time. The big question was, how fast is it decelerating? Two independent teams went after that by using Type 1a supernovae as standard candles. These are exploding white dwarfs that reach nearly the same peak brightness every time, so by measuring how bright they look, you can figure out how far away they are. They measured distant supernovae in galaxies billions of light years away, compared their distances to how fast those galaxies were receding, and expected to see signs that the expansion was gradually breaking. Instead, the supernovae came out dimmer than expected. Dimmer meant farther away than a slowing universe allowed. The only way to make the data fit was to accept a very strange conclusion. The expansion of the universe is not just continuing, it's accelerating. On large enough scales, galaxies are being pushed apart faster and faster over time. That leaves you with a brutal follow-up question. What could possibly push entire galaxies apart against their own gravity? Normal matter can't do it, dark matter can't do it, it only adds more gravity. To make space accelerate in its expansion, you need something that acts like a repulsive component built into space itself. In Einstein's equations, there's a term you can add that behaves exactly like that, called the cosmological constant. You can think of it as a constant energy density filling space everywhere. As the universe expands and there's more space, the total amount of this energy increases, even though the density stays the same. Gravity from matter and dark matter tries to pull things together, but this extra component pushes the fabric of space apart. On small scales, like galaxies and clusters, gravity still wins, matter stays bound. On very large scales, across hundreds of millions of light years, this dark energy dominates and drives acceleration. It's not pushing galaxies through space like rockets, it's changing how space itself evolves. Here's the part that should bother you the most. This dark energy is not a minor correction. When you fit all the data, dark energy makes up roughly 68% of the universe's total energy content. Dark matter is about 27%. Normal matter, all the atoms in stars, gas, dust, planets, and your body, is the leftover 5%. The thing that dictates the long-term fate of the universe is not galaxies or black holes. It's this smooth, mysterious component that you don't understand. What is dark energy? It might be a true cosmological constant, a fixed property of the vacuum, meaning empty space is never really empty. It always carries this tiny energy density. It might be a new field, something that can change slowly over time. It might be a sign that general relativity itself needs modification on the largest scales. Right now, you don't know. What you do know is that whatever dark energy is, it behaves in a consistent way across many different types of observations, and ignoring it makes the data fall apart. That raises another important question. How do you actually measure the history of cosmic expansion well enough to claim that it's accelerating and not just misreading a few supernovae? The answer is that you don't rely on one method. Supernovae are one tool. Another are what are called standard rulers, physical scales imprinted in the universe that you can measure at different times. One key standard ruler comes from baryon acoustic oscillations, which are fossil traces of the sound waves that moved through the hot plasma of the early universe, the same waves you saw encoded in the cosmic microwave background. When the universe cooled and atoms formed, those waves froze in as slight over and under densities in the matter distribution at a characteristic scale. Over billions of years, galaxies formed more often in those overdense regions. Today, when you map the positions of millions of galaxies, you see a slight excess of galaxy pairs separated by that same preferred distance. Because you know roughly how big that scale is in physical units, you can use it as a ruler. By seeing how large it appears at different redshifts, you can infer how the universe has expanded over time. Combine that with type 1a supernovae distances and with the cosmic microwave background, and you get a consistent picture. All three agree that the universe transitioned from a decelerating phase, when matter dominated, to an accelerating phase, when dark energy took over. The numbers you get for the dark energy density from each method line up within uncertainties. That consistency is hard to fake. Once you accept that dark energy is real and currently dominant, you're forced into one more big question. What does that mean for the future? What's the endgame? If dark energy is truly a cosmological constant, a fixed property of space that doesn't change with time, then the universe will keep accelerating. Distant galaxies will move away faster and faster, and more of them will cross your cosmic horizon, the distance beyond which light can never reach you. In tens of billions of years, an observer bound to something like the local group will see a small region of galaxies. Everything else will have faded out of view, redshifted and pushed beyond contact. Star formation will slow, galaxies will age, and the universe will slide towards a big freeze, cold, dilute, and mostly empty, with only local structures left. If dark energy is not constant, things get stranger. If its strength grows with time, you can end up with a big rip scenario. In that case, the expansion rate accelerates so violently that it eventually overcomes not just the gravity holding clusters together, but the forces binding galaxies, then star systems, then even atoms. In the most extreme models, there's a future moment where every bound structure is torn apart by the runaway expansion of space itself. Current data don't demand that future, but they don't completely rule out evolving dark energy either. You could also imagine more exotic possibilities. Dark energy might slowly decay into something else, changing the rules again in the far future. But right now, the best fit is a universe where a smooth, invisible energy component already controls the large-scale dynamics, and will keep doing so. So step back and look at the picture you have built. Normal matter is 5%. Dark matter is the invisible skeleton that holds galaxies and clusters together. Dark energy is a property of space that decides how fast everything is being pulled apart. To understand what dark energy is stretching and what dark matter is shaping, you now need to look at the universe on its largest scales, not at single galaxies or clusters, but at how everything is arranged over hundreds of millions of light years. When you do that, you find that the universe is not a random sprinkle of galaxies at all. It has a pattern, a vast connected structure that shows you exactly how gravity and dark matter have been sculpting space for billions of years. When you think about galaxies on the biggest scales, it is easy to imagine them just sprinkled around at random, like dots on a blackboard. But that is not what the data shows. When you zoom out to hundreds of millions of light years, galaxies line up into a structure that is very organized and very strange. Large surveys like the Sloan Digital Sky Survey have mapped the positions of hundreds of thousands of galaxies. When you plot them in 3D, you see long filaments, sheets, and dense knots with huge empty-looking regions in between.
Clusters and superclusters sit at the intersections of these filaments, and the gaps are tens of millions of light years across. On these scales, the universe looks less like a random scatter and more like a gigantic web or foam, with galaxies arranged along threads and walls around big voids. So, how do you get something that complex, starting from the nearly smooth early universe you saw in the cosmic microwave background? The key is gravity, and the fact that most of the matter doing the pulling is dark. Computer simulations start with tiny density fluctuations, like the small hot and cold spots in the CMB, and then let gravity act over billions of years in an expanding universe. If you include only normal matter, gas and stars, you do not get the right result. Gas pressure and radiation wash out too much structure. When you include dark matter as a cold, collisionless component, the picture changes. Dark matter feels gravity, but not light or pressure. It starts to clump first, forming small overdensities that grow and merge into larger halos and filaments. Normal gas falls into that skeleton, cools, and forms stars and galaxies in the dense regions. When you compare the output of these simulations to real galaxy surveys, the match is striking. The same web pattern appears, with filaments, nodes, and voids on the same scales. What you see in the sky is basically the bright, thin layer of normal matter tracing out a much more massive, invisible dark matter structure underneath. If matter is collecting along filaments and in knots, that means something else is happening between those structures, something most people never think about: the voids themselves. Cosmic voids are not small gaps. They can be 100 to 300 million light years across. They're not completely empty, but their density of galaxies is far below average. There are still some small galaxies, some gas, some dark matter, but compared to the filaments and clusters, they are almost deserted. Imagine dropping the entire Milky Way into the middle of one of these deep voids. The nearest large galaxy could be hundreds of millions of light years away. Your night sky would change completely. Instead of a bright, rich band of the Milky Way, you might see only a faint spread of stars from your own galaxy and almost nothing beyond. No bright nearby galaxies, no dense galaxy clusters, very few external features. From that location, the universe would look much more empty than it does from where you are now. Voids are just as real a part of the cosmic web as the crowded regions, and they remind you that, on the biggest scales, empty is a key part of the structure. You might think, fine, the large-scale pattern is fixed and galaxies just ride the overall expansion as space stretches out. But that is not the whole story. On top of the smooth Hubble expansion, where more distant galaxies recede faster, galaxies also have their own local motions called peculiar velocities. They stream along filaments toward the dense nodes, pulled by gravity. These bulk flows can reach hundreds of kilometers per second, while the Hubble flow sets the baseline recession. That means a galaxy's actual velocity is a combination of the universal expansion and its local fall into nearby overdense regions. On small and intermediate scales, that local motion can partially cancel or add to the apparent expansion, so some galaxies can seem to be moving toward us even in an overall expanding universe. For precision cosmology, you have to separate these components, but those same flows are also a tool, because they show you how matter is distributed and how strong gravity is in different directions. The cosmic web is not a static pattern. It's a dynamic system, with galaxies constantly sliding along its strands into deeper gravitational basins. So, where are you in all of this? Your galaxy is not just floating alone. It sits inside a larger flow field with a name: Laniakea. The Milky Way, together with the local group and many other nearby clusters, belongs to a region called the Laniakea supercluster. This region extends over roughly 500 million light-years. It's not a single solid structure, but a volume within which galaxies tend to flow to a common center of attraction. If you trace the motion of thousands of galaxies around us and subtract the smooth Hubble expansion, you see that their peculiar velocities point towards certain regions where mass is concentrated. One of these regions has been called the Great Attractor.
When analysts analyze these flows in detail, they define Laniakea as the set of galaxies whose motions are directed toward the same gravitational basin, separated from neighboring basins by boundaries where the flow lines diverge. The Milky Way sits on a relatively small branch near the edge of this giant valley, like being on the side of a huge valley system. Locally, gravity from the surrounding mass distribution is pulling us and our neighbors inward. On larger scales, dark energy is still driving the overall expansion, dragging everything farther apart. Both effects act at once. You are in a galaxy moving at hundreds of kilometers per second through space, inside a filament, inside Laniakea, inside the cosmic web, inside an accelerating universe dominated by dark energy. So, at this point, your picture of the universe is this. A nearly smooth early plasma grew tiny fluctuations into an enormous, three-dimensional web of dark matter and galaxies, with crowded knots and wide empty voids. Those structures are still evolving, still flowing, still merging. And whenever the densest regions of that web, like galaxy centers and compact objects, move and collide, they do more than just rearrange matter. They actually shake space-time itself. That shake is not light, it's not particles, it's something more fundamental. And now, you are finally ready to look at the universe in a completely different way, not by what you see, but by what you can hear in the fabric of space-time. What does it actually mean for the universe to shake, and for you to measure that shake from a lab on Earth? Gravitational waves are not sound waves moving through air or gas. They're ripples in space-time itself, traveling at the speed of light, about 300,000 kilometers per second, roughly 186,000 miles per second. Whenever massive objects accelerate, especially in extreme systems like two black holes or two neutron stars spiraling together, they disturb space-time and send out these waves. As a gravitational wave passes through you, it stretches space very slightly in one direction and squeezes in the perpendicular direction, then reverses, over and over. Distances between free-floating objects grow and shrink by tiny amounts. For strong astrophysical events, by the time the wave reaches Earth, that fractional change is around 1 part in 10 to the power of 21. Over a 4-kilometer distance, that's a stretch of a few times 10 to the minus 18 meters, far smaller than the size of an atomic nucleus. So, you're trying to detect a change in length that tiny caused by something that happened maybe a billion light years away. The obvious question is, did anyone actually pull that off? In 2015, the answer became yes. The LIGO project, with 2 detectors in the United States, picked up a clear signal from 2 black holes merging about 1.3 billion light-years away. Each black hole was around a few tens of solar masses. As they orbited, they sped up, circled each other hundreds of times per second, then merged into a single, larger black hole. In a fraction of a second, roughly 3 times the mass of the Sun was converted into pure gravitational wave energy and radiated away. For that short moment, the power output in gravitational waves from that merger was higher than the combined light from all the stars in the observable universe. You did not see it with your eyes, but LIGO recorded the characteristic chirp as the frequency and amplitude of the wave rose, then cut off when the black holes merged. This detection, announced in early 2016, was the first direct observation of gravitational waves, predicted by general relativity almost a century earlier. It confirmed that black hole binaries exist in nature, and that space-time really does ripple the way the equations say. To do that, LIGO relies on a simple idea pushed to an extreme. Each detector is an L-shaped interferometer with 2 arms, each 4 kilometers long, about 2.5 miles. A laser beam is split and sent down both arms, bounced back and forth between suspended mirrors many times, then recombined. If the 2 arm lengths are exactly the same, the returning light waves cancel in a specific way at the detector. If a gravitational wave stretches one arm and squeezes the other, even by a tiny fraction, the timing of the returning light changes and the interference pattern shifts. The challenge is that the change in length is incredibly small, about 1 part in 10 to the power of 21. Over 4 kilometers, that is a change of less than 1,000th of the diameter of a proton. To see that, LIGO has to isolate its mirrors from vibrations, from earthquakes, traffic, wind, and even thermal motion of atoms. The whole system operates under vacuum with advanced seismic isolation and precision control of the laser. When you see a detection, you are literally looking at a graph of the universe's stretching and squeezing as a wave passes through Earth, registered as a slight mismatch in two 4-kilometer light paths. Gravitational waves on their own are already powerful, but their real strength appears when you combine them with light. In 2017, LIGO and the Virgo detector in Europe picked up a different kind of signal, one that lasted much longer, consistent with two neutron stars spiraling together. This event, called GW170817, came from about 130 million light-years away. About 1.7 seconds after the gravitational wave signal ended, a burst of gamma rays hit space telescopes, coming from the same region of the sky. Over the next hours and days, optical, ultraviolet, X-ray, and radio telescopes around the world observed a bright, fading source in that galaxy. That single event gave you multiple types of information at once. The gravitational waves told you the masses of the neutron stars and the energy lost as they merged. The light showed you the radioactive glow of heavy elements freshly created in the ejecta, confirming that neutron star mergers can forge gold, platinum, and other heavy nuclei. The delay between the gravity wave and the gamma rays let you compare the speed of gravitational waves to the speed of light, and they matched extremely closely. The distance and redshift together gave an independent way to estimate the expansion rate of the universe. This is what people mean by multi-messenger astronomy. Not just light, not just gravity, but both, locking down the physics from different angles. If you can already do this with 4-kilometer arms on Earth, the next step is obvious. You build even more sensitive detectors and you take the experiment off the planet. Future ground-based observatories, like planned third-generation detectors, aim for longer arms and better isolation, which will widen the volume of space you can monitor and extend the range of masses and frequencies you can hear. In space, missions like LISA will put 3 spacecraft millions of kilometers apart, forming a triangle that acts as an interferometer. With such long arms, you will be sensitive to much lower frequency waves than LIGO can detect. Those low-frequency waves come from different systems, like supermassive black holes merging in the centers of galaxies, or a compact object spiraling slowly into a huge black hole. You might even detect a background of gravitational waves from processes that happen in the very early universe, long before the cosmic microwave background was released. Instead of only seeing the universe in light, you will be listening to its deep bass signals, the slow, powerful rumbles that carry information about the biggest structures and the earliest times. So now you know this. The universe does not just shine, it also rings. Black hole and neutron star collisions send out ripples that stretch Earth by less than a proton's width, and you have built machines precise enough to notice. But the violent events that make those signals are not gentle processes. They are tied to the universe's most extreme explosions, events that can outshine entire galaxies, build the elements in your body, and in some cases, threaten any life unlucky enough to be nearby. The next step is to look directly at that violence, at the supernovae and gamma-ray bursts that rewrite their surroundings in a single catastrophic blast. What actually happens when a star dies badly enough that it rewrites its whole neighborhood in a single blast? You have seen stars quietly burn for billions of years, but the most massive ones don't go out gently. They end in events so violent that for a short time, they can outshine entire galaxies and change the chemistry of the universe. Take a massive star, roughly 8 to 50 times the mass of the Sun. For most of its life, it holds itself up by fusing lighter elements into heavier ones in its core. Fusion pushes out, gravity pulls in, and the star stays in balance. But eventually, the core builds up iron and nickel, elements that don't give you net energy when you fuse them. Once enough iron accumulates, fusion stops supporting the core. Gravity wins in seconds. The inner regions compress, and in many cases, protons and electrons combine into neutrons, forming a neutron star. That sudden halt and collapse, plus an intense flood of neutrinos, drives a powerful shockwave back out through the star's outer layers. This shockwave rips the star apart. The resulting supernova can briefly outshine an entire galaxy. We're talking about total energy output of around 10 to the power of 44 joules or more. Shock fronts race through the star at thousands of kilometers per second, tearing it to pieces and flinging the outer layers into space. That debris is not just random gas, it's enriched material, full of elements that the star made during its life and in the explosion itself. Even a normal core collapse supernova is extreme, but there's another class of event that takes that violence and compresses it into seconds, and in a focused beam. Those are gamma ray bursts. Some GRBs release as much energy in a few seconds as the sun will emit over its entire 10 billion year lifetime. The energy is not isotropic. It's focused into narrow jets moving at more than 99.9% of the speed of light. Within those jets, conditions are so extreme that most of the power comes out as high-energy gamma rays. If a long-duration gamma ray burst went off within a few thousand light-years of Earth and one of its jets was pointed directly at us, it could seriously damage our atmosphere. Models suggest it could deplete the ozone layer and flood the surface with harmful ultraviolet radiation. There's debate about how likely that is, but the basic point stands. These are not minor events. They are powerful enough in the right geometry and distance to affect entire planets. For now, the GRBs we've seen are much farther away, so they're a warning, not an immediate threat. You can push even further into the extreme end with hypernovae and collapsars. Some very long GRBs and very energetic supernova-like events seem to come from massive stars that collapse directly into black holes, with accretion disks and jets forming almost immediately. In these models, the core collapses, a black hole forms, and material around it feeds in and powers jets that punch through the remaining star. These jets can drill their way out and then keep going into space, carrying enormous amounts of energy in narrow cones. The term hypernova is used for supernovae that are significantly more energetic than typical core collapse events. Collapsar refers to this direct collapse into a black hole plus jet scenario. Not every hyperenergetic burst fits neatly into a single category, but the trend is clear. Some dying stars release orders of magnitude more energy than a normal supernova, tightly focused, and they do it in environments already rich with gas and dust. Locally, that kind of event can carve out cavities, shock nearby clouds, and trigger new waves of star formation. On top of that, there's a subset of supernovae that crank up the brightness even more, the so-called superluminous supernovae. These are about 10 to 100 times brighter than typical supernovae at their peak. They can reach absolute magnitudes around -20 or brighter, which means they're visible across billions of light-years with modern telescopes. There are a few leading ideas for what powers them. One idea is that a newly born magnetar, a rapidly spinning neutron star with an enormous magnetic field, dumps its rotational energy into the expanding supernova ejecta, keeping it hot and bright for much longer than usual. Another idea is that the explosion slams into a very dense shell of gas around the star, maybe material the star threw off before it died. The collision converts kinetic energy into light very efficiently. Either way, you get an explosion that stays bright over a long time from a host galaxy that might be faint or hard to see otherwise. These events are rare, but because they're so bright, you can spot them far out into the universe and use them as probes of star formation and galaxy evolution in the distant past. All of this sounds like pure destruction. Stars blowing themselves apart, jets blasting through space, shockwaves scouring their surroundings. But here's the key. Without that violence, you do not get the building blocks for complex chemistry or for life. The core of a massive star is where elements like carbon, oxygen, silicon, and up to iron are assembled through fusion. Some heavier elements can form in the explosion itself, in the rapid capture of neutrons during the supernova, or in the aftermath of neutron-star mergers. Those elements then have to be spread into space. Supernova are the main dispersal mechanism. When a star explodes, it ejects its enriched material at thousands of kilometers per second. That gas mixes with the surrounding interstellar medium. Future generations of stars and planets form out of that enriched gas and dust. The oxygen in your lungs once sat in the core of some star. The calcium in your bones was fused in a previous generation of stars. The iron in your blood came from supernova and from neutron-star mergers. Even elements like gold and platinum, as you saw earlier, are linked to extreme events like kilonova.
So every time a galaxy has a burst of star formation, followed by waves of supernova and occasional GRBs, it is not just losing stars. It is upgrading its material. The overall metallicity, the fraction of mass and elements heavier than helium, goes up. That richer chemistry allows for more complex molecules, better cooling of gas clouds, and more diverse planetary systems. The same explosions that could wipe out life in a nearby system are the reason life can exist at all in the long run. You now have a universe where stars live, explode, and recycle their guts into new stars and planets, all while black holes merge, neutron stars collide, and space-time itself vibrates with the fallout. But that chaos does not just happen out there. The rules that govern these extreme events, especially relativity, are part of the tech you use every day. Even something as basic as the navigation in your phone only works because engineers quietly correct for the fact that time itself does not tick at the same rate everywhere in the universe. Right now, without you noticing, your phone is quietly correcting for Einstein, or it would just be wrong. The GPS system only works because engineers treat relativity as a practical engineering problem, not a theory from a textbook. GPS satellites orbit Earth at about 20,000 kilometers altitude, moving at roughly 14,000 kilometers per hour, around 8,700 miles per hour. At that height and speed, time on the satellite does not tick at the same rate as time on the ground. Two effects compete. Special relativity says moving clocks run slower, so the satellite's motion makes its clock tick a bit slow compared to a clock at rest on Earth. General relativity says clocks deeper in a gravitational field tick slower, so the satellite, higher up in a weaker gravitational field, has its clock tick faster than one on Earth's surface. When you put the numbers together, the gravitational effect wins. The net result is that a GPS satellite's clock runs faster than an identical clock on the ground by about 38 microseconds per day. 38 millionths of a second sounds tiny, but GPS works by measuring how long it takes a radio signal, moving at light speed, to get from satellite to receiver. Light travels about 300,000 kilometers per second, so even a microsecond error means a position error of hundreds of meters. Stack up uncorrected 38 microseconds every day, and your GPS position would drift by kilometers per day. Receivers would quickly become useless for navigation. So the system is designed with relativity built in. The satellite clocks are adjusted so that once they are in orbit, their tick rate matches ground time as seen by users. Without that relativistic fix, every "where am I" request from your phone would gradually become nonsense. That same principle, gravity changing the pace of time, applies everywhere, not just to satellites. In Earth's gravitational field, clocks higher above the surface tick slightly faster than clocks lower down. The difference between your feet and your head is tiny, nanoseconds over a day, but with precise atomic clocks, we can measure it. If you put one atomic clock at sea level and another a few thousand meters up a mountain and let them run, after a while, the mountain clock will be ahead. You literally age a tiny bit faster on the mountain than at sea level. The difference is way too small to matter to your day-to-day life, but it is real, it is measured, and it tells you that time is not a single universal flow. It depends on how deep you sit in a gravitational well. Now flip to the other main ingredient in relativity, motion. From your point of view, a moving clock runs slow. If you sit on Earth and watch a spacecraft fly by at a significant fraction of light speed, its onboard clock ticks slower compared to yours. At 0.9 times the speed of light, around 270,000 kilometers per second, around 600 million miles per hour, time dilation is already big. A trip that lasts 1 year according to the ship's clock might correspond to more than 2 years on Earth. If the crew turns around and returns, they come back younger than the people who stayed home, not just a few seconds, but by years. The key point is that there is no adjustment you can make that cancels this in a simple way. The faster you go, the more extreme the effect. At speeds close to light speed, time on board can be slowed by large factors. From the crew's perspective, their heartbeat, their metabolism, everything feels normal. Their seconds are still seconds. But when they compare with Earth's clocks later, they see that far more Earth time has passed. The universe allows you to trade distance and space for distance and time in a very asymmetric way. You can move forward in your own proper time while skipping ahead relative to people who stayed in your home. Put gravity and motion together and you get some of the strangest situations near compact objects, especially black holes. Close to a black hole, say a few Schwarzschild radii from the center, the gravitational field is extremely strong. General relativity says that time for an observer hovering there, somehow holding station with a huge rocket, would pass much more slowly than for someone far away in weak gravity. From the perspective of the hovering observer, the outside universe would seem sped up. Stars would orbit faster, distant clocks would race ahead, processes far away would unfold in compressed time. Meanwhile, a distant observer watching something fall toward the black hole sees the opposite. As the object approaches the event horizon, its clock appears to slow down. The light from it gets redshifted, stretched to longer wavelengths, and its motion seems to freeze near the horizon. The infalling object, from its own frame, crosses the horizon in finite time and continues inward. But from far away, you never quite see it cross. You just see a fading, slowing image. Time near a black hole and time far away are not just out of sync, they're warped relative to each other in ways your everyday intuition does not handle. You might be tempted to ask, with all these different ticking rates, what is the real time for the universe? When cosmologists say the universe is about 13.8 billion years old, they're not using your wristwatch or a clock on a galaxy near a black hole. That number is defined in a particular frame, a kind of averaged cosmic rest frame. You can think of it as the frame in which, on very large scales, the universe looks roughly the same in every direction, and the cosmic microwave background radiation looks as uniform as possible. In that frame, you can define a cosmic time coordinate and say, at this cosmic time, the universe had this temperature, this density, these structures. Locally, though, everyone's proper time is slightly different. Your clock on Earth, a clock on a GPS satellite, a clock on a fast-moving spacecraft, a clock near a neutron star, all count seconds differently because of gravity and motion. There is no single master clock that everyone must agree on. There are many clocks, each following its own path through spacetime. The age of the universe, you quote, is really a convenient average measure tied to that special large-scale frame, not an absolute number that every observer everywhere would agree on if they could compare. So here is where you stand now. You live in a universe where time is elastic, where your phone navigation quietly fixes for relativity, where moving fast or sitting deep in gravity changes how quickly you age compared to someone else, and where the age of everything is a carefully defined quantity, not an obvious one. All of that is happening in a universe that is still extremely young compared to what is coming. The stars you see now are temporary. The galaxies you see now are temporary. The current balance between matter and dark energy is temporary. The next step is to push your timeline forward, not by millions or billions of years, but by trillions and beyond, and ask a blunt question. If nothing new intervenes, how does a universe like this actually end? So far, everything we've talked about lives in a young universe, one that is only 13.8 billion years old. That sounds old to you, but on the scales that really matter, this is early childhood. If nothing radically new appears in physics, the universe has a clear long-term direction, and it is not toward more light and structure, it is toward darkness and simplicity. Start with stars. Right now, galaxies like the Milky Way are still forming new stars out of cold gas clouds, a few solar masses of new stars per year. But the supply of cold gas is finite. Every time a star forms, every time one explodes as a supernova, more gas gets locked into long-lived stars or heated and blown out into intergalactic space where it is hard to cool and collapse again.
Over the next tens of billions to hundreds of billions of years, the rate of star formation drops. Big, short-lived blue stars disappear first because they burn through their fuel in a few million years. The universe gradually shifts from one filled with many bright young stars to one dominated by faint, low-mass stars and the leftovers from earlier generations, white dwarfs, neutron stars, and black holes. In that future, the key players are small stars. Red dwarfs, with less than half the sun's mass, are extremely efficient. They burn hydrogen slowly and can live for trillions of years, far longer than the universe has existed so far. Brown dwarfs, objects too small to sustain normal hydrogen fusion, already fill space now, but they are faint and hard to detect. Over trillions of years, they will quietly cool, radiating away their heat. In the very distant future, any surviving planets will see a night sky that is nothing like yours. The bright band of the Milky Way, the obvious external galaxies, the rich clusters, all of that will fade. The sky will be lit mainly by dim red dwarfs and the occasional afterglow of a white dwarf or a distant remnant, faint reddish points instead of bright blue-white stars. As time keeps rolling, stars keep evolving. After roughly 10 to the 14 to 10 to the 15 years, that is 100 trillion to a quadrillion years, most ordinary stars will have finished their lives. The universe will be in what is often called the era of degenerate stars. Degenerate here is a physics term. It means matter supported by quantum pressure, not normal gas. The main objects will be white dwarfs, neutron stars, and black holes, plus cold brown dwarfs and rogue planets drifting in the dark. White dwarfs will gradually cool, turning into dark, cold remnants, sometimes called black dwarfs, not to be confused with black holes. In this era, the universe is not completely static. Binary systems, where two remnants orbit each other, slowly lose energy by emitting gravitational waves. Orbits shrink over extremely long timescales, and some pairs will merge. White dwarfs that merge reignite nuclear reactions and explode in delayed supernovas. Neutron stars that merge create kilonovas and heavier elements. Black holes that combine release bursts of gravitational radiation. But these are rare flashes in an otherwise dim universe, brief events separated by enormous stretches of quiet darkness. Go to even longer times and black holes start to dominate the landscape. Over extreme timescales, up to about 10 to the 100th years, black holes are the main long-lived structures. They swallow stars, gas, dust, and even other black holes. At the same time, quantum effects at the horizon make them leak energy slowly through Hawking radiation. As they radiate, they lose mass, shrink, and their temperature rises, so they radiate faster. For stellar mass black holes, the evaporation time is around 10 to the 67th years. For supermassive black holes, the times are even extremer, with a 1 followed by up to 100 zeros in years. During this black hole era, most of the remaining matter and energy is locked inside black holes of different sizes, slowly evaporating. Occasional encounters and mergers still happen, but as time goes on, those events become rarer. Eventually, even the largest black holes lose enough mass that evaporation runs away. In their final stages, they radiate more intensely, then disappear, leaving behind only a bath of low-energy particles and photons drifting in an ever-expanding space. This is the approach to heat death, a state of maximum entropy, where energy is spread out as evenly as possible and there are no significant free energy gradients left to drive complex processes. No heat engines, no chemistry, no new structures forming. On these timescales, structure is not just rare, it's effectively gone. All of this assumes that dark energy behaves like a constant, the same cosmological constant that seems to be driving the current acceleration. If that stays fixed, the expansion keeps speeding up in a predictable way, galaxies beyond your local bound region drift out of view, and the universe asymptotically approaches a cold, dark, dilute state. But if dark energy changes with time, the script could be very different. If it grows stronger, you could get a big rip, where the expansion rate accelerates so much that eventually it tears apart galaxy clusters, then galaxies, then star systems, and finally even atoms.
If dark energy decays into something else, the acceleration could slow or reverse. New physics at very late times could produce phenomena we have no current way to predict. Right now, with the data you have, the simplest model, a constant dark energy, fits well. That model points to a universe whose long-term trend is a slow fade into darkness and simplicity, over timescales so large that trillions of years are just the opening act. No new stars, no active galaxies, no black holes, just a very cold, almost empty cosmos where nothing interesting happens on any human or even stellar timescale. So here is the tension. You live at a very special time. Stars are still forming, galaxies are bright, planets exist, chemistry is active, and on at least one world, complex life is asking these questions. The universe will not always be like this. The window where heavy elements, stable stars, and complex structures coexist is finite. That leads to one last brutal question. In a universe this large, this old, and heading toward that kind of future, what are the odds that life like you ever appears at all? And why are you seeing the cosmos now, during this brief bright phase instead of in the long dark eras before or after? Here's the last uncomfortable question. In a universe this huge and this old, what are the odds that you even exist at all? Start with the basics. Earth sits about 150 million kilometers from the sun, around 93 million miles, in the zone where liquid water can stay on the surface. Not too hot so it all boils off, not so cold that it all freezes solid. It feels special, it has a Goldilocks label on it in every school diagram, but zoom out and that setup is not rare by design. You know there are hundreds of billions of stars in the Milky Way, and billions of them are roughly sun-like. Exoplanet surveys show that planets are common, and Earth-sized planets in temperate zones are not exotic. They show up a lot. Statistically, just inside this one galaxy, there are probably billions of rocky planets sitting in their star's habitable zone with the right amount of light for liquid water. That means the basic physical conditions for something Earth-like are not a freak accident. They are a standard outcome when you let gravity build stars and planets for long enough. But having a planet in the right zone is just step one. The next step is what you are made of, and that part reaches back through almost every topic we've covered. Hydrogen in your body, especially in water, is primordial, straight from the Big Bang. But almost everything else you need was built later. Carbon, nitrogen, oxygen, phosphorus, sulfur, the key elements for biochemistry, were forged in the cores of multiple generations of stars and in the shock waves of supernovae. The iron in your blood likely came from the core of a massive star that died long ago, maybe thousands of light years away, and was thrown out at thousands of kilometers per second in an explosion. Those elements mix into gas clouds, which eventually collapse into new stars and planets. The rock under your feet is star debris. The air in your lungs is star debris. Your DNA is assembled from atoms cooked in other systems, spread by explosions, and reassembled here. That means life on Earth is not just happening in the universe, it is made from the universe's own recycled parts. So you have a lot of potential planets, and the right ingredients show up naturally over time. The real question is, how long does it take for those ingredients to arrange into something alive and aware? Look at Earth's timeline. The planet formed about 4.5 billion years ago. The earliest clear signs of simple life appear over 3 billion years ago. For almost all of Earth's history, life was single-celled, microscopic. Complex multicellular life, things with tissues and organs, only shows up in the last few 100 million years. Humans, and anything you would call intelligent civilization, are a thing of the last few 100,000 years, with modern technology compressed in the last few 100 years. So it took about 4 billion years to go from simple cells to complex animals, and then to you. Now compare that to cosmic time. The universe is about 13.8 billion years old. Stars like the sun will keep forming for trillions of years, especially long-lived red dwarfs. That means you're not near the end of the story. You're right at the beginning. The universe has burned less than 1% of the total star time it will likely have. If intelligent life can form on many worlds, there's a good chance that most of it will arise far in the future, around stars that haven't even formed yet. Right now may be early in the life-friendly window, not late.
That leads directly into the Fermi paradox, the sharp version of the "where is everyone" problem. You have a galaxy with hundreds of billions of stars, probably hundreds of billions or trillions of planets, billions of those in habitable zones, and the timescale where life has billions of years to get started. Even if the odds per planet are low, you would still expect a lot of hits. Civilizations that are even a little ahead of you could, in principle, send probes, build large structures, or leave other detectable marks across the galaxy over millions of years. But when you actually look, you don't see clear, unambiguous signs of advanced civilizations. No obvious engineered megastructures, no artificial beacons you can confirm, no galaxy-sized energy users that stand out in surveys. The sky looks natural, so something is off. Maybe life itself is rare. Maybe simple life is common, but the jump to complex, intelligent life is extremely unlikely. Maybe intelligent life tends not to last long, wiped out by its own technology, by environment collapse, or by random disasters, so overlapping, long-lived civilizations are rare in time. Maybe advanced civilizations don't broadcast loudly, or they hide, or they move into forms you don't know how to detect. Or maybe you just haven't been looking with the right tools in the right places for long enough. Right now, you don't have an answer. You only know that the physical stage is huge, the time available is huge, and yet the part of the stage you can see looks empty of obvious, loud neighbors. That tension is not solved, it's open. And until you solve it, you live with a strange possibility that your pocket of awareness might be rare, at least right now, even if the basic conditions for life are common. All of that loops back to one last point. You aren't sitting outside the universe, observing it from a safe booth. You're built from it. Hydrogen from the Big Bang, heavy elements from dead stars, arranged into cells, tissues, and the nervous system that can think about expansion, dark matter, dark energy, black holes, and cosmic fate. Right now, atoms that were once in the core of a star or in the blast of a supernova are running code in your brain trying to understand the sky. When you measure redshifts, you're tracking the universe stretching. When you map the cosmic microwave background, you're reading its baby picture. When you detect gravitational waves, you're listening to its collisions. When you study exoplanet atmospheres, you're checking whether other worlds have the right conditions for chemistry and maybe biology. You're taking a universe that would go on whether anyone watched it or not and turning it into something that can be described, modeled, and understood. So here's where you end up. In a universe that's bigger than you can really picture, older than any human story, dominated by dark components you barely understand, heading toward a slow, cold future with no guarantee that intelligence is common. Yet for a brief window, on one small planet around one average star, matter has become aware enough to ask what all of this means, and to build instruments that can see all the way from the afterglow of the Big Bang to the death of stars and the fate of time. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.